Hi, in this today's session we will see the Gauss theorem. Now a Gauss theorem gives you the relationship between the total flux passing through any closed surface and the net charge enclosed within that surface. So to prove this Gauss theorem, let us consider an isolated positive charge placed in the space. Now here we are interested in the relation between the electric flux and the charge. So to calculate the electric flux, we need to count the number of electric field lines crossing a unit cross sectional area. So here in this case, if you want to calculate the total electric flux due to this charge Q, you need to bring a surface area into the picture. So here let me just consider a sphere of a radius r, which is enclosing this charge Q in a such a way that the center of the sphere is exactly coinciding with the location of this Q. Now here the surface which is enclosing this charge Q is said to be the Gaussian surface. Now all that we know is that the magnitude of the electric field due to this positive charge shows a spherical symmetry, which means is that if you just try to calculate the electric field at any point on the surface of that hollow sphere, you will be getting the same electric field, or else the strength will be the same. So the expression to calculate the electric field at any point, say r, from the point charge, we have the expression is, let me write the statement: electric field at any point on the surface S. So S be the total surface of this sphere, so let this be the S. We have a expression, the electric field E will be equal to 1 upon 4 pi epsilon naught into Q upon R square. Now here we are interested in the electric flux. Now if you see the direction of the electric field lines due to this positive charge, they will be pointing radially outward. Alright, and again the electric flux is nothing but the number of electric field lines crossing a cross sectional area, that is your flux. So here to calculate the total flux, what I can do is that I can just take a very small section of this sphere to study it, and then in general I can apply it to all the part of the spheres. So what I am trying to do is that let me just divide this entire surface area of this hollow sphere into small pieces, into n number of pieces, and in that case I'll be getting n number of small area element, correct? So let me just consider any one of that area element just to study. So here let this be the small area element delta S, which I choose on the surface of this hollow sphere, and let R be the distance from the center over here. So in that case, if I want to calculate the electric flux through this small area element, we have an expression from the last class is that the electric flux which is phi E, represented as phi of E, is nothing but the vector E dot vector ds, which is a smaller area element, correct? Now here the same expression I can just write it as E dot ds into cos theta, where theta is the angle between the electric field lines and the unit vector of this plane small area element. Now here in this case, if you just see the direction of the electric field line is pointing radially outward, and we know how to calculate the electric field at any point, okay, in that space using this expression. So that will give you the magnitude. Now what about the direction? Okay, so to calculate the flux, electric flux, okay, we need a magnitude of the electric field and the magnitude of the surface area and the angle between them, right? Electric field and the unit vector of the surface area. So here, if you just see, okay, I can just say that the electric field in this case, let me just write the electric field E, vector E, is equal to, I can write it as the magnitude of this electric field into the direction in which it is facing. So I just take that from the center to the surface area element. This is the radius of my sphere. Okay, and if I just want to show the direction of the electric field with respect to this r, I can just put it as r cap. Correct? So that this is the vector form of my electric field. In the same way, if I just try to write the vector form, okay, of ds, vector ds, this will give me the magnitude of that. So this is a very small area element, surface area, into the direction. If you see, it should be always normal to that planar surface area. So which is again pointing, okay, in the same direction as of the electric field. And electric field, I have written it with respect to the r, radius. So again, this will be a r cap. Now, if you see these, they are unit vectors, they are in the same direction, right? That means both the directions are parallel to each other. So here in this case, if you just see the theta, okay, both are pointing in the same direction, so there is no angle. So here in this case, the theta, what you will be getting is 0. So what I just can say is that, I'll just rewrite this expression phi of E, that phi of E will be equal to E dot ds into cos of 0. The angle between both this is 0. Correct? And cos of 0 is 1, and that will give me the flux is equal to E dot into ds. Now this is the expression, okay, what we have got for the electric flux, okay, for a small area element. Now this is for a small area element, okay, but we need to calculate the total flux, which is coming out from this surface area, right? So in that case, the same expression, I can just rewrite this as for a n number of small pieces, because I just divided into a small area element, right, n pieces. So in that case, I can just write the phi of E will be equal to summation of, all, I can say, delta S, all the small piece of that area element into E dot ds. All right, so this is the expression. Or the same expression, I can just again rewrite this as, I can just write this phi of E will be equal to, if I just put a limit summation going from the delta S, suppose it's tends to very, very small, okay, tends to 0, in that case, the number of n will be going to infinite. In that case, again, I can write it as the E dot ds, which I can rewrite in the form of the entire surface integral, so which will look like the surface integral S into E dot ds. So that's the other way of writing this. Now let me use this expression, okay, the expression for this phi of E, okay, which will give me the total electric flux passing through this entire surface area. So in that case, what we have a relation is this, what I have got, the expression, if you see, the phi of E is equal to surface integral S into vector, it's a magnitude of E into ds. Now here the magnitude of the electric field, we know what is the magnitude of the electric field. It's a 1 upon 4 pi epsilon naught into q upon r square. Yes. And what is the surface integral? The surface integral, okay, is nothing but the total area of this sphere, and that is given as 4 pi r square. So 4 pi r square. So square. Now here the 4 pi and 4 pi will get cancelled. R square and r square will get cancelled. Correct? And what is left here is the phi of E. I can just write the phi of E will be equal to Q by epsilon naught. So that's the final expression that you will be getting. So this is the Gauss law, which says that the total electric flux passing through any closed surface is equal to 1 by epsilon naught times the total charge enclosed within that surface. Now, a few points regarding this Gauss law is that the Gauss law is valid for any closed surface of any shape and size, because if you just see this relation, you don't see any term which is related with the shape or a size of this Gaussian surface. So that's the first point. The second point is that if you have, say, a charges, say, Q1, Q2, Q3 lying inside the Gaussian surface, in that case, the small q over here will be just the net electric charge, inside this Gaussian surface. Now here, suppose you have a few charges lying outside this Gaussian surface, say over here or here. In such cases, the electric field, whose flux is over here on the left hand side, is due to both the charges which are lying outside the Gaussian surface plus the charges which are inside the Gaussian surface. So that's for the left hand side, but again here in the same case as well, this Q only measures the total electric charge, just inside the Gaussian surface. So it will not count these charges which are lying outside the surface. So that's the important point. Now here, while drawing the Gaussian surface, you see that the Gaussian surface does not pass through a discrete charges, because the electric field, due to a system of discrete charges, is not well defined at the location of that any charge. So that's the reason. But a Gaussian surface can pass through a continuous charge distribution. So no problem in that. Now here, the advantage of the Gauss law is that it makes things easier while calculating the electrostatic field when you have a system of charges which are symmetrical in nature. So that's one advantage of this. So here we will see the applications of the Gauss law in the next class. But now let's see some problems, which will help us, to clear the doubts, regarding this Gauss law. So let's see the problems. Now here in this question, a cylinder is placed in a uniform electric field with its axis parallel to the field, and we are told to show that the total electric flux through the cylinder is 0. So here in this question, the electric field given to us is the uniform electric field, and the cylinder is placed in such a way that the axis of the cylinder is exactly parallel with the direction of the electric field. Now here we are interested in the total electric flux. So here we have expression to calculate the electric flux. Now in this case, it's a cylindrical surface. So what I can do is that I can count, or else I can just calculate the electric flux, which is for this plane surface, and then for this, and then for the curved surface of the cylindrical surface, right? So here in this case, so let me just say integral of vector E dot vector ds. So let me just calculate the electric flux for this cross-sectional area. So let me just say it is my left plane surface, In the same way, let me just calculate the integral of vector E dot vector ds for this right plane surface. So in this case, let this be my right plane surface and a electric flux through this curved surface. All right, so this is my cylindrical curved surface. Now here the same expression, okay, let us try to calculate the individual flux for these cross-sectional areas. So here in this case, okay, for the left plane surface, so how do we calculate? In this case, what I can do is I can just for an example, okay, let's just consider a small section, okay, of this. Let this be the planar element, okay, small area element. Now here in this case, if you just see the electric field, the direction of the electric field is pointing towards the right? So here in this case, the electric field will be pointing towards the right. While if you just see the direction of this surface area will be pointing towards the left. So that's the direction of this unit surface area. So let me just say this is the direction of your ds vector, right? And the same expression I can write it as is equal to vector E dot ds can be written as E dot, I can just say the integral of E dot ds into cos of theta, and this theta is nothing but, if you see, it's a 180 degree over here, exactly anti-parallel to each other. So when I substitute the cos of 180 degree in this case, so let me just take this theta to be of 180 degree plus the electric flux for this cross-sectional area. Now here in this case, again I can just say, let me choose a small area element, and here the unit vector of this area element will be pointing radially outward. Yes, so you just draw normal which is pointing radially, normally outward in that case. So here this is the direction of your surface area which is pointing outward, and let this be my ds vector. Now if you see the direction of the electric field, which is exactly in the same direction as of this, so the electric field is also in the same direction. So here in this case I can just say that E dot ds will be equal to cos of 0, the angle between them is 0. While for this third surface area, which is over here, if I just choose, this is your small plane area element, in this case the direction of this surface area will be pointing outward like this, so this is your ds vector. And if you see the direction of the electric field, which is again from left towards the right, and that's the electric field direction, and here it's a 90 degree, you are getting the angle is a 90 degree. So in this case I can just say the integration of E dot ds and cos of 90. So cos of 180 is your -1. So in this case what I'll get, cos of 180 is -1, so which I can write it as minus E. Yes, and integral of ds, okay, this is for a very small area element. Now here integral of ds means I am interested in the entire surface area of this, and this is a circular plane, right? And if you know the area of this surface circular plane is nothing but pi r square. So I can just write this as my pi r square. So that will give me integral of ds plus, again here E dot ds, I can say it's a cos of 0 will give you 1 into the E, so this will be the E, and once again the integral of ds, the plane, again this is a circular plane, right? So that will be giving me pi r square. While in this case cos of 90 is your 0, so this will be 0. And now if you see the total electric flux, so this is phi of E. So here the total electric flux will be equal to this, and this will get cancelled. Yes, minus E pi r square plus pi r square, and this will be a 0. So I can say this will be a 0. So thus we have proof. Okay, so that's the answer for this, which says that the phi of E is equal to 0, which means is that if you just look at the Gauss law is phi of E is equal to Q by epsilon naught, which means is that there is no charge over here inside this Gaussian surface that we have chosen. Now here in this question, the figure shows, okay, the phi charged lumps of plastics and electrically neutral coin, and here the cross section of the Gaussian surface is shown, and we are told to calculate the electric flux through this Gaussian surface, where we are given a charge Q1 and Q4 are your positive charge of 3.1 nanocoulomb, where the charge Q2 and Q5 are your negative charge of 5.9 nanocoulomb, and the charge Q3 is again a negative charge of 3.1 nanocoulomb. So here to calculate the electric flux to the Gaussian surface, we know the phi of E is equal to 1 over epsilon naught times the total charge enclosed in that Gaussian surface. So here this is the main formula. Now if you see, look at this, the charge Q, it is just the addition of all the electric charges only which are inside this Gaussian surface. So here in this case, the total flux, the phi of E, will be equal to the charge Q1, which is inside the Gaussian surface, the charge minus Q2. So let me just say it's the plus Q2 plus the charge Q3, which is inside this Gaussian surface, divided by the epsilon naught, while this charge Q4 and Q5 is not taken up. Okay, so while calculating the electric flux for any Gaussian surface, you see that you are taking the charges which are just inside the Gaussian surface. And here this is your 1 rupee coin, and which is electrically neutral. So here this is your neutral, so no charge present on this coin. So in that case I can just add these charges. The Q1 given to us is of positive 3.1 nanocoulomb, so 3.1 into 10 to the power minus 9 coulomb, plus again the charge Q2, which is minus 5.9 into that will be a negative charge. So here in this case it will become minus 5.9 into 10 to the power minus 9 coulomb, and the charge Q3 is also a negative charge whose value is 3.1 into 10 to the power minus 9. Again it's a negative charge, right? So divided by epsilon naught, is the value for epsilon naught is 8.85 into 10 to the power minus 12. Now if you solve this, okay, you will be getting the expression as 3.1 minus 5.9, okay, minus 3.1 into 10 to the power minus 9. I take that out common, divided by 8.85 into 10 to the power minus 12. Here in this case, this and this will get cancelled, correct? So what is left is minus 5.9 into 10 to the power minus 9 divided by 8.85 into 10 to the power minus 12. And when you will solve this, you will be getting the answer. The phi of E will be equal to minus 666.67 into 10 to the power 6.6667 Newton meter square coulomb minus 2. So that's the answer that you will be getting, the total electric flux through this Gaussian surface. Now here in this question, okay, the S1 and S2 are the two hollow concentric spheres enclosing a charges Q and 2Q respectively, okay, as shown in this figure. And here we are given a two question. The first is, what is the ratio of the electric flux through S1 and S2? So let's see this. So here we need to calculate the ratio of the electric flux of S1 and S2. So let's go with the first question. Now here these are your two hollow concentric sphere S1 and S2. So let's calculate the electric flux through the first sphere. So in that case it will be a charge enclosed by this concentric sphere S1. So it's just a Q, okay, that is inside this sphere S1. So in this case it will be a capital Q by epsilon naught. This is for sphere S1. In the same way, I can calculate the electric flux for the sphere S2. Now when I consider the sphere S2, it will be enclosed, it is enclosing the charge Q plus the charge 2Q, right? So in this case it will be Q plus 2Q divided by epsilon naught for the surface S2. Now here I am interested in the ratio, so what I can do, I can just take the phi of E due to the S1, okay, and the phi of E due to the second, let me say 1 and 2. In this case it is Q by epsilon naught divided by Q plus 2Q, that's both are positive charge. So in this case it will be a 3Q by epsilon naught. So here Q by epsilon naught and Q by epsilon naught will get cancelled, and what you will be left is 1 over 3. So the ratio of this is 1:3. So I can say that the ratio of phi of E1, okay, is to phi of E2 is 1:3. So that's the ratio of the electric flux. So that's for this first question. Now let's see the second question. In a second question it says, how will the electric flux through the sphere S1 will change if a medium of dielectric constant, say of 5, is introduced in a space inside S1 in place of air. So what we have calculated is for the air, okay, or else you say vacuum. Now here suppose you are introducing one dielectric medium and that value of that K, okay, is equal to 5. So in this sphere S1 you say that the dielectric medium is inserted and whose value is 5. Now if you see the phi of E is equal to, right, it's just the integral of vector E dot vector ds. That's the expression, right? So this is for the vacuum case. Now when you have a dielectric medium, in that case the electric field will get reduced by this much value. So in this case when you have a dielectric constant, okay, so it's a constant, I can just take 1 over K out, and that will be an integral of vector E dot vector ds. So that's the expression. And here vector E dot vector ds, okay, you will be getting, it's the same, okay, I can just replace this as Q by epsilon naught. So it's a 1 over K into, I can just write this as Q over epsilon naught. So only modification to this, the Gauss law, is that when you have a dielectric medium, you just multiply this denominator with a K. So that is the change in the equation. Now here what you know is that the phi of E, the flux phi of E, will be equal to, the K value is 5, so, and Q is what? Capital Q. So this will be a Q upon phi times the epsilon naught. So this is the change that you will see, okay. Here in this case it's a Q by epsilon naught. But when you introduce a dielectric medium, in that case, this answer will get reduced by 5. So this is the formula that you need to remember. So that's the answer for both the questions. Now here in this question, the electric field components is given. So here when I see this, there is only electric field in the x direction, and the magnitude of that electric field is given to us is alpha into square root of x, where the magnitude of the electric field, okay, along the y and z direction is given to us is 0, okay, and here the alpha value is given to us is 800 newtons per coulomb, square root of meter, and we are told to calculate the flux through this cube, and the second question is to calculate the charge within that cube. So here the electric field that is given to us is along the x direction. So let me just show the electric field. So this is the direction of the electric field, which is pointing in the positive x direction. All right. So now here we need to calculate the total flux through this cube. Now before going for the total flux, okay, let me write the formula first. So we are having the flux phi of E is equal to vector E dot vector ds into ds, which I can write the same formula as to be as E dot ds into cos theta, correct? Now here this cube, if you see, has got 6 faces. That's a top face, bottom face, front, back, and left and right. Now we know that when the angle, okay, so these are your surface area, right? This is the top surface, bottom surface. Now we know that when the angle between the electric field and the unit vector of the surface area is 90 degree, then we have the flux through that area is 0. So here in this case, if you just consider this top surface whose unit vector is pointing upward and which is exactly perpendicular with the electric field line, that means the flux through this top surface is going to be a 0, correct? So that's one thing. In the same way, if I just take this front face, again it is also, the front face is along the z-axis, right? The unit vector of this front face is along the z-axis, so which is again perpendicular to the x-axis. So again it is 0. In the same way, if I just see the bottom surface, again it is going to make a 90 degree with this x-axis, so that's a 0. The back surface over here, again it will be a 0, 90 degree. So altogether, all the 4 faces, the top face, the bottom face, and the left and the right face, the flux through that surface area will be a 0. So only contributing the surface will be this, the front surface. So this is the surface that we are interested in. Okay, so these are the surfaces. Now here let's try to calculate the flux through both the surfaces. So in this case, the total electric flux will be equal to integral of, okay, I can say E dot ds into cos theta. So this is for the left surface, plus the integral of E dot ds into cos theta, so that is for the right surface, right? Only 2 surfaces will be contributing. Now here the electric field that is along the x component is given to us is alpha x square root of half. So in this case I can just say that, okay, or else let me just go with the theta first. For the left surface, if you just see, the electric field is along the x direction, positive x direction. But when you see the unit vector of this surface it is pointing towards the left, right? So this is the n cap of the left surface, or else the back surface, I'll say. Okay, let us consider the left surface. So here in this case, if you just see the direction of the electric field is towards right, so that's the direction of the electric field. And if you just measure the angle between this, both the vectors, it will be a 180 degree. So here in this case, I'll just write that electric field E is constant, okay, into integral of ds into cos theta is how much? It's the 180 degree, cos of 180. Same way, plus I can just take the electric field out, integral of ds into cos, here this surface, the right surface, let me call this as the right surface. So in this case, if you just see the direction of the unit vector is pointing outward, and it is again in the same direction as of the electric field. So n cap of r. So in this case, if you just see the angle between the electric field and this n cap of r is 0, so that will give me a cos of 0. So cos of 180, what I know is a negative minus, correct? And electric field that is given to us is alpha square root of x. So let me write this as alpha, okay, into square root of, let me just say x of half, and integral of ds, that means I'm interested in the entire area of this surface. And if you know this is a cube of having a side of a, and I'm interested in this surface area, so I can just write it as a square, correct? So it will be a square, and cos of 180 is taken minus. Now in the same way, I can just write this as a cos of 0 is 1, and that's the electric field given to us is alpha into x of square root of x into integral of ds. Again, this surface area, the side I can just multiply and I will get the area of this square. So area of the square is what? A into a, that will give me a square. Now here, this is the x, even this is the x. Now this is for the left surface, right? And we have chosen a coordinate over here which starts from the origin O, and the distance at which this face is, I can just take from 0 to a. So here this x I'll be replacing by a. So I can just write it again as minus alpha. X is how much? A. The left plane surface, from the origin at a distance, and that will give me a square root into a square plus alpha, okay, into, this is the distance at which the right plane, okay, is at. So 0 to a, this is at your a. So that means again this is at your a distance. So this will be overall will be a 2a distance. So I can replace this x by 2a, and that is a square root into a square. So that's what I'm getting. Now here the value of the alpha, let's substitute it afterwards. Okay, now here let me rearrange this expression. So here I see that the alpha is common, all right. So I can just take the alpha term out from here. So let me just take this alpha, and even if you just see this, a raised to 1 by 2 plus a raised to 2, okay, or else let me just multiply this a first minus alpha. This will give me a raised to 1 by 2 plus a raised to 2. I can just take the LCM, okay, cross multiplication. So that will give me a 2 2s are 4, 4 plus 1 is 5, 5 by 2, 5 by 2 plus alpha, again this is what? 2 into a to the power, okay, it will be a 5 by 2. So again, let me just take that 2, okay, I'll just write the 2 square root of 2, and a I'll write it as separate, it will be a 5 by 2, correct? Just add this. Now from here I can take the common out. So what I am left with is the alpha will be taken out, into a to the power 5 by 2 is the common term, and I can just say that it will be a square root of 2 minus 1. So this is the answer. I take this over here. When I multiply, open up this, I'll get the same result. So now I have got the final expression to calculate the electric flux through the cube. So that's the expression. Now here I can substitute the value of alpha. Alpha is given to us is 800. So let us substitute. It has 800 into the A that is given to us is 0.1 meter. So 0.1 meter. So it's a 5 by 2 into square root of 2 minus 1. And if you just solve this, okay, numerical, you will be getting the phi of E. The phi of E is equal to 1.05 Newton meter square coulomb minus 1. So that's the answer that you will be getting. Now here we are told to calculate the charge within the cube, and to calculate the charge within the cube we have a relation. Okay, if I just rearrange the same expression of a Gauss law, which is Q is equal to, okay, I can just say that it will be the electric flux into the epsilon naught, just rearranging this. And here I can just write the value of this phi of E is how much? 1.05 into epsilon naught value is 8.85 into 10 to the power minus 12. Okay, and that will give me the answer to be of 9.27 into 10 to the power minus 12 coulomb. So that's the value of the charge, okay, which is available inside this cube. So that's the answers for the question. Now here in this question we are given again a uniform electric field which is in a positive x direction for positive x, and same uniform electric field with the same magnitude, okay, is in the negative x direction for negative x. And here this is the value of the electric field, which is equal to 200 I cap, okay, newtons per coulomb for x greater than 0, and vector E is equal to minus 200 I cap newtons per coulomb for x less than 0. And here a right circular cylinder of length 20 centimeter and radius 5 centimeter has its center at the origin, okay, and its axis is along the x-axis, you know, so that the one face is at a 10 centimeter, okay, away from this O, and the other face is at again at a 10 centimeter but on the negative side of this coordinate. Now here this is the length of your cylinder, and here we are told to calculate, you know, in the first question the net electric flux, you know, through both the flat surfaces. So here there are two flat surfaces. Second question is to calculate the electric flux to the curved surface, and the third question the net electric charge enclosed by this Gaussian surface. So that is asked. Now here to get the first answer, you know, what we have to do is that the net flux is given to be as the phi of E is equal to vector E dot, you know, I can just say that delta S, correct? So let me just calculate it for the left side first, okay, so let this be for the left side plus the vector E dot delta S for the right side. So these are the two things. So let me just say E for the L, okay, and this is for the right side. This is a flat surface towards the right. Now here the electric field for the left side that is given to us is, I can just point it outward, it's along the negative axis. E is equal to minus 200 I cap. So that's the direction of the electric field for this face. And here if you just see the unit vector of this surface area, which is also pointing in the same direction as of the electric field. So this is the direction of the surface area. Now here I can just write this electric field as vector E of the left face is given to us is minus 200 I cap into the vector delta S of the left face. I can write it as delta S into the unit vector, okay, so that is n cap of L, and which is again in the negative direction, right? So this is the origin, this is the positive x-axis, this is the negative x-axis. So this will give me a minus n cap of L. In the same way, I can just have a term for the right face. Here in this case, the electric field, if you see, is pointing E is equal to 200 I cap, which is along the positive, and the unit vector of this surface is also pointing towards this. So which is given as, I can write it as n cap of R, which is along the positive x-axis. So here I can just say that electric field is 200 I cap into, I can write this vector delta S as delta S into the n cap of R. So that is. Now here if you just multiply this minus into minus, that will give me a plus, right? So here I can say 200 I cap into delta S. Delta S is nothing but the surface area of the left face, and which we calculated as pi r square. So the formula to calculate this is pi r square, and the area that the radius is given to is 5 centimeter. So I need to convert it into meters, and here in this case I can just say that, okay, into 3.14 into, I'll just say multiply by 3.14 into 0.05 the square. So that's the answer, where I cap and minus n cap of L, both are in the same direction, so angle between them is 0. All right, so that will give me a scalar quantity when I multiply. In the same way, this is your 200 I cap into n cap, both are in the same direction, theta is equal to 0, that means the cos of 0 is what? 1, into delta S. Delta S is how much? 3.14 into 0.05 the square. So this is your r square, pi into r square, and that will give me the answer to be of, if you just solve this, so the answer that I'll be getting is 1.57 Newton meter square into Coulomb inverse. So that's the answer. No, I think, yeah. So this is for the left side, plus 1.57 into Newton meter square Coulomb minus 1, and the total answer that you will be getting for both this, when you add, we are told to net, so 1.57 plus 1.57, that will give me the answer to be of 3.14 Newton meter square Coulomb inverse. So that's the answer what I'll be getting. Now we have got the first case. What about the second case, the flux to the curved surface? So electric field is given to us only in the x direction, right? And here if you just consider any area element, it will be exactly perpendicular to this electric field. Theta is equal to 90 degree, that means there will not be any flux through this curved surface. So in this case, for the answer, the question 2, it will be a 0. Why? Because theta is equal to 90 degree. So I can say this is my first one. For the second one, I can say theta is equal to 90. So the phi of E will be equal to 0. Whereas for the third case, the charge inside the cylinder, in the third case, I can just say the Q is equal to phi of E into epsilon naught. Phi of E, what we have got is 3.14. 3.14 into epsilon naught is 8.85 into 10 to the power minus 12, and that will give me the answer to be as 2.78 into 10 to the power minus 11 Coulomb. So that's the answer for the charge which will be available inside this cylinder. So that's the answer. Now, what you take home today from today's session is the Gauss theorem, which says that the total flux through any closed surface is equal to 1 over epsilon naught times the net electric charge enclosed by that surface, and which can be written as something like this. Now here, this Gauss theorem is very important because it makes the things easy while calculating the electrostatic field for a symmetrical charge configuration, which we will see in the next class. So thank you very much.